from the title, you know that in today's tape, we are going to talk about properties of matrices. But we're going to talk about things just as important. We're going to talk about the concept of proof. Proof is a very important part of linear algebra. Proof is a very important part of all mathematics. In fact, mathematics is based upon the axioms and the theorems that you can generate from the axioms. You have to prove the theorems. Today's proof is basically just one of translation. We're going to also talk about illustrations, and you need to get the difference between a proof and an illustration. And then we'll do a proof by counterexample. So you need to understand what it means to find a counterexample, how to find a counterexample, and you need to understand that you can prove something false by finding a counterexample. But any number of examples will never prove anything true. We'll start with some basic definitions. The zero matrix has all zeros as its elements. So we could have a 2 by 3 zero matrix that had 2 rows and 3 columns, all consisting of zeros. The identity matrix I is a square matrix that has 1s along its main diagonals and zeros elsewhere. For the 3 by 3 identity matrix, I3, that means I for 3 by 3, would be 1, 0, 0, 0, 1, 0, 0, 0, 1. It's a square matrix, 3 by 3, that has 1s along its main diagonal and zeros elsewhere. Now we're ready to talk about the properties of matrices. Let A, B, and C represent matrices, and let little c and d represent scalars, which would be real numbers. For all of the properties, assume that dimensions allow the indicated operations. In other words, when we have the operation of addition, assume that the two matrices to be added have the same dimension. For multiplication, assume that the columns of matrix 1 match the number of rows for matrix 2. The first property is the commutative property of addition. In other words, matrix A plus B is the same as matrix B plus A. You can add the matrices in any order. Matrix 2 is the associative property of addition. I can add matrices B and C and then add A and get the same answer as I would if I added A and B and then added C. That's the associative property. Property 3 is a type of associative property involving scalar multiplication. If I have 2 scalars C and D, I can multiply the scalars and then multiply by the matrix and get the same answer as I would if I multiplied the scalar by the matrix and then multiplied by the second scalar. 4 is the associative property of the distributive property of scalar multiplication. The distributive property of scalar multiplication. This side tells me to add A and B and then multiply by C. I can get the same answer by multiplying C times A and then C times B, and then performing the addition. So I distribute the C over matrix A and matrix B. And I can distribute the matrix over the scalars. So C plus D times A, I can multiply the A with the C to get the CA, A with the D to get the DA. So these are your two distributive properties. You can distribute the scalar, you can distribute the matrix. A plus a 0 matrix is A for all matrices. A plus its opposite is 0. If a scalar times a matrix is equal to 0, then either the scalar is 0 or the matrix is a 0 matrix. This is the associative property of matrix multiplication. If I'm multiplying three matrices A, B, and C, it doesn't matter which grouping I use. I can group B and C and multiply B times C and then multiply by A. Or I can group A and B, multiply A times B, and then multiply by C. I get the same answer either way. Here's the distributive property of matrix multiplication, whereas I can distribute the matrix A over the matrix B and the matrix C. The distributive property of matrix multiplication. And I can either left distribute or right distribute. C times the scalar C times matrix AB will give the same answer if I multiply the scalar by A and then multiply the matrix CA by B. That's kind of an associative property. And it doesn't matter which matrix I multiply the scalar with. I can multiply it with A or I can multiply it with B. A times the identity element is A. Now I stands for the identity matrix, which is the matrix with ones on the diagonal and zeros elsewhere. And the identity matrix times A is A. That's where it really got its name, identity matrix. You multiply A by the identity and get identically the same thing. Well, let's look at one of the proofs. Let's look at proof of property 4. Now, I'm not going to prove all of them for you. I'm going to prove a couple just to get you used to how to do proofs. Let's go back to property 4. And this was the distributive property of scalar multiplication. So we have the scalar C multiplied by matrix A plus B. So I'll start with the left side, C times A plus B. Well, I can rewrite this as C times, and I can write A as a matrix consisting of the A ij's and B as a matrix consisting of the B ij's. Because remember, this is how I denote the elements in matrix A. Matrix A would be the elements in row 1, or row I, column J. Well, to add matrices, which I do the adding first, I add corresponding elements. Well, these are the corresponding elements, so I would have C times A ij plus bij. Now, I really just have the one matrix here. Well, to multiply C by a matrix, I multiply C by all the elements. That would be C, Aij, plus C, Bij, well, since to add matrices you add components, I can break it up and get C, Aij, plus C, Bij, which is the same as C times Aij plus C times Bij, which, as you recognize, is simply CA plus CB. So we've completed the proof. I started with the left side. C times A plus B. I ended with the right side. CA plus CB. Now I want to do an illustration for you. Now an illustration is when you do an example trying to convince yourself that it's true. And let's look at an example, an illustration of property 9. Property 9 is matrix, just that matrix multiplication is associative. So I'm going to illustrate that one. That is that A times BC is equal to AB times C. Well, let's just get examples, and I'll do an easy case. Let's let A be the matrix 1, 0, 2, negative 3. Let's let B be the matrix 1, negative 4, 0, 1. And let C be the matrix 1, 2, 0, 1. Well, for an illustration, I'm going to work it on both sides and show I get the same answer. So first, let's do A times BC. So that's going to be the matrix 1, 0, 2, negative 3 times B 1, negative 4, 0, 1 times C 1, 2, 0, 1. Now, based on the parentheses on the left, I do the B and C first. So it's going to be 1, 0, 2, negative 3 times 1 times 1 is 1, negative 4 times 0 is 0, so this is going to be 1. 1 times 2 is 2, minus 4 is negative 2. 0 times 1 is 0, 1 times 0 is 0, 0 plus 0 is 0. 0 times 2 is 0, plus 1. Now I do this multiplication. 1 plus 0 is 1. Negative 2 plus 0 is negative 2. 2 plus 0 is 2. Negative 4 minus 3 is negative 7. So when I multiply B times C and then by A, I get this matrix. Now let's go back and do it the other way, in which I do AB first and then C. So multiply A, 1, 2, 0, -3, by B, 1, -4, 0, 1, times C, 1, 2, 0, 1. So we're doing the grouping AB times C. AB times C. Do what's in the parentheses first. 1 plus 0 is 1. -4 plus 0 is -4. 2 plus 0 is 2. A -8 minus 3 is -11. Now I need to multiply that by 1, 2, 0, 1. 1 plus 0 is 1. 2 minus 4 is -2. 2 plus 0 is 2. 4 minus 11 is -7. Let's look back and see if we got the same answer as we did on the first problem. 1, -2, 2, -7, so you can see they are equal. So we have illustrated 9. We illustrated it with an example. Of course, one can never prove that a property is true by an illustration. You simply can't do it. You might find 9 million examples that seem to work, but you still haven't proved that it's true. You might convince yourself that it's true. You might be so sure that it's true that you will use it in everyday life, but you can never prove something is true by an illustration. Illustrations are primarily to convince you that it's probably true, so then you'll look for an actual proof. However, one can prove that something isn't true by finding a counter example. Proves that matrix multiplication is not commutative. Well, now, one cheap way would just be to prove that it's a mismatch in one way and you can't multiply. But I'm going to use 2 by 2 matrices and actually produce a counterexample. Let's let A be the matrix 1, 2, 3, 4. And let's let B be the matrix 5, 6, 7, 8. Well, let's multiply A times B, and then we're going to multiply B times A. 5, 6, 7, 8 times 1, 2, 3, 4. So I'm going to multiply A times B, then I'm going to multiply B times A. And my goal is to show that they're not the same. We're multiplying A times B. 1 times 5 is 5, plus 14 is 19. 1 times 5 is 5. 2 times 7 is 14. 14 plus 5 is 19. 1 times 6 is 6. 2 times 8 is 16. 16 plus 6 is 22. 3 times 5 is 15. 4 times 7 is 28. 28 and 15 is 43. 3 times 6 is 18. 4 times 8 is 32. 18 and 32 is 50. Now let's multiply these. 5 times 1 is 5, plus 6 times 3 is 18. 18 and 5 is 23. 5 times 2 is 10, plus 24 is 34. 7 plus 24 is 31. 14 plus 32 is 46. Are they the same? Obviously not. So matrix multiplication is not commutative. Let's look at another proof. Let's prove that C times AB is equal to A times CB. Now for proof, you have to use a general case. So I'm going to multiply C times, for matrix A, I'm going to say it's a matrix having elements A, IJ, times B, IJ. B will be the matrix having elements Bij. Well, how do I do this matrix multiplication? Remember, I had to go out the row, down the column, but we had a way of writing that. So that's going to be the matrix A, I1, B, 1J, plus A, I2, B, 2J, plus out to A, IN, B, N, J. So that's how you multiply the matrices. This is the definition I gave you last time. Well, I can multiply C by the elements. So that's going to be C, A, I1, B, 1J, plus C, A, I2, B, 2J, plus C, A, IN, B, N, J. Now I can use, these are all just real numbers now. C is a real number. Aij is the entry in matrix A, row I, column 1. Bij is the entry in matrix B, row 1, column J. So these are all just real numbers. Since they're just real numbers, I can reorder and regroup any way I want to. In particular, I can write it as A, I1, C, B, IJ, plus A, I2, C, B, 2J, plus A, IN, C, B, N, J. Again, the reason I can do that is the C, the AI1, Bij are all just real numbers. So all I'm doing is working with real numbers. We know the real numbers are associative and commutative, so I can change the order of the grouping basically any way I want to. But now, using the rule for adding and multiplying matrices in reverse, this would be the matrix A, Ij, times the matrix C, B, ij, which is A, ij, matrix Aij, times C times the matrix B, ij, because I can factor a scalar out of a matrix, which is A times C, B. And we've proved it. Sometimes the computer can be used to help convince ourselves that a property is true. As an example, let's use derive to verify the 2 by 2 case of property number 11, which is the right-hand distributed property for matrix multiplication over matrix addition. A plus B times C is equal to AC plus BC. So we're just going to use derive to verify the 2 by 2 case. We'll start by authoring 3 matrices. So I'll author matrix A, which is A, B, C, D, matrix B, which is E, F, G, H, and matrix C, which is I, J, K, L. So to make it easy, we just went up the alphabet A, B, C, D, E, F, G, H, I, J, K, L. So this would be the general 2 by 2 case. So in essence, we're doing a proof on the 2 by 2 case, but not a general proof. So now if we look at the left side, A plus B times C, it's going to be matrix 1 plus matrix 2 times matrix 3. In fact, that's how I went to derive, hit author, hit expression, and said number 1 plus, or parentheses, number 1 plus number 2, close parentheses, times number 3. So I have a matrix A plus B times matrix C. A plus B times C. And then I told derive to simplify. And it gave me AI plus BK plus EI plus FK and so forth. So that's here's the matrix that it gave me. Then I told derive to do A times C plus B times C. AC plus BC. And again, derive simplified gave me the answer. And if we compare the two, we'll see they are the same. AI, BK, EI, FK, AJ, B1, EJ, F1, CI, DK, GI, HK, CJ, DI, GJ, HI. They're all the same. Except I think these were L's that I call I's. But anyway, we can see that they are identical. So derive verified the 2 by 2 case for property 11.